Today we're going to look at mole calculations and exam questions and break them down into simpler tasks so that we can actually answer the questions and look at how difficult some of the questions are worded and break them down into easier, manageable chunks. So the first question is all about titanium ore. So it's given us the percentage of iron, percentage of titanium, and then we've got to work out what's remainder is oxygen. So the remainder is 100, because it's 100%, minus what have we got for iron, 36.8, plus we've got that much titanium. So what's left over, pop that in your calculator and you should get 31.6% is oxygen. So then we move down, so that's a nice easy one to ease you into the questions, and then we now move into moles. Now it's asking us for moles, and we know that moles equals grams over AR. So always write that at the side so that you remind yourself what to do. So it's given us an example here of how to do it. The number of moles of iron is grams of iron over the AR of iron. And you might think, well, we haven't got grams. Well, we've got percent. So with percent, assume we have 100 grams. So in 100 grams, we've got 36.8 grams of iron. So therefore, if we divide that by the AR, we have moles of iron. Do the same for the titanium. We've got 31.6 grams. Divide that by the AR of titanium, which is 48. And that gives us 0.66 moles of titanium, and you can see it's the same number of moles as iron. Move down to oxygen, and we've just worked out that we've got 31.6 grams of oxygen in 100 grams. Divide that by 16, which is the AR of oxygen, and we get 1.98. Okay, so now we've got 2 marks. Now, the next question is, what is the simplest ratio for the moles of atoms? So this is our empirical formula, the simplest whole number ratio. So 30, we've got 0.66 moles of iron, 0.66 moles of titanium, and 1.98 moles of oxygen. How do we turn that into the simplest whole number? We divide it by the smallest, which is 0.66. So that's everything. So that gives us 1, and that 1.98 divided by 0.66 is 3. So now we've got this mark. So transferring that into the formula, what is the formula? We've got 1 iron, 1 titanium, and 3 oxygens, FeTiO3. Now we've got that mark. Question 2 is a bit harder now, so we're going to break this down. So here we've got grams, 5 grams. So we know if we've got grams, we can work out moles. But it says it's an impure lead nitrate, so there's going to be some impurities in here. And the volume of oxygen formed was 0.16 dm cubed at RTP, room temperature and pressure. And the impurities did not dissolve. What is the percentage of lead nitrate in the sample? And you might look at this and think, oh my goodness, it's too difficult. Let's just break it down. The thing that you need to know is that 1 mole of gas, any gas, occupies 24 dm cubed. So the question has broken it down for you to make it easier so that you can work out the steps. So how can we work out the number of moles of oxygen formed? Well, we know that 0.16 dm cubed, if we divide that by 24, because we know that 1 mole occupies 24 dm cubed, so 0.16 dm cubed times divided by 24 is the number of moles. Here's the equations that you need for this. Moles equals volume over 24 for dm cubed, Or if you've been given centimetres cubed, you can do the volume of the gas divided by 24,000, and then that will give you moles. So 0.16 divided by 24 is, put that in your calculator, we're going to keep it to at least three significant figures, 667. So now we've got to relate that to the moles of lead nitrate. Now here, this is where your balance symbol equation is going to help you here. So we know that 2 moles of lead nitrate make 1 mole of oxygen. So we've worked out the moles of oxygen. So all we've got to do is multiply that by 2. So that should still be in your calculator. So multiply that by 2 and you should get, keep it, oops, I made a mistake there, 0.133. Keep it all in your calculator, write down on the exam paper to 3 significant figures. We'll work out significant figures at the end. Don't round too early, otherwise you'll end up the wrong answer. Keep it all in your calculator if possible. For the next part, you need this equation, moles equals grams over MR. They've been nice to us here, they've given us the MR. Here, we don't need to work that out. So if we had to work that out, that would have been worth an extra mark as well, but at the moment we've only got 4 marks here. So what's the mass then? So we've got moles now, we've got MR, we can rearrange that equation and we can work out what the mass is. So we've got, be careful, make sure it's use this one, 0.0133 moles of lead nitrate, times that by 331, and you should get 4.41 grams of lead nitrate. Go back to the original question. So we took 5 grams, heated it up, and in that was only 4.41 grams of lead nitrate. The rest of it was impurities. So express that as a percentage. So 4.41 grams divided by 5.00 times 100, because it's percent, and you should get 88.3%. I kept it to 3 significant figures, and I've kept everything in my calculator all the way through, so you shouldn't have any errors carried forward if you do that. Now, as a last check, I quickly scan the question, make sure it doesn't say give your answer to 2 significant figures. It doesn't, so I'm going to leave it at 3 significant figures. So that's all 4 marks there. Next question is a titration question. So there's a bit of blurb about metals, Group 1 metals as being soluble. And so here we have, we're going to make crystals of lithium chloride by titration. So here we've got hydrochloric acid in the burette, and we've got lithium hydroxide in the conical flask. So here's our acid, and here's our base. And we've got an indicator in there. So the first part of the question is asking you, how can you obtain a neutral solution of the lithium chloride which does not contain an indicator? Because the main purpose of this is actually to make the lithium chloride salt, pure salt. So there are 2 ways we can do this. We could either add charcoal, activated charcoal, or activated carbon to remove the indicator, and then we'd have to filter out the activated charcoal. Or the most common method is to repeat the experiment without an indicator using the same volume of the acid. So you would do the titration, work out the volume of acid needed to neutralise the 25 mils of lithium hydroxide. Once you know the volume required to neutralise, you repeat the whole thing but don't have the indicator in there, and just add that exact volume. So say that volume was 22.6 mils of acid, then you add 22.6 mils of acid to another volume, 25 mil volume of lithium hydroxide. Don't add the indicator, and then you know you've neutralized it completely. So you can see here what I've written, that would have given me 2 marks. So repeat the experiment without the indicator is the first mark, and using the same volume of acid is my second mark. Now let's go on to part 2 of this question. It says you cannot prepare a neutral solution of magnesium chloride by the same method. How would you prepare a neutral solution of magnesium chloride? There are many ways to do this. We could either add magnesium metal to a known volume of hydrochloric acid, and we would just keep adding magnesium metal until no more magnesium would dissolve. So it would fizz, it would get hot, because it's an exothermic reaction, and we just keep adding it and add it and add it in, so that's adding it in excess until no more reacts. And then we know that all the acid has been used up. So therefore, we now have a neutral solution, because the question's asking us to make a neutral solution. So you have to keep adding the magnesium until there's no more fizzing, and you can see the magnesium metal unreacted. And then we've got a neutral solution. We've made magnesium chloride. All the hydrochloric acid's been used up. Filter off the unreacted magnesium, and then you would have your magnesium chloride salt. And then you could heat that up to evaporation point and make crystals like that. But that's not what it's asking us for. It just wants to prepare a neutral solution. So the first mark is add magnesium metal to hydrochloric acid until no more dissolves, or add it in excess, and then filter to remove the unreacted solid. You don't have to use magnesium metal. You could use magnesium carbonate. You could have magnesium oxide, or even magnesium hydroxide. So any of those would react with the hydrochloric acid to make the salt magnesium chloride. So here you can see this would have got me 3 marks then. So the first mark is add the magnesium metal or magnesium carbonate to the HCl until in excess. That's the second mark. And then the third mark would be filter the excess unreacted solid. So we've got our 3 marks there. Now we come to the titration calculation part. You can see I've just drawn a quick picture here. I would recommend you do that. It takes about 3 seconds, so you can work out what you've got in your burette is 2.20 moles per dm cubed, and we know the volume was 20 mils of the acid. We know that the lithium hydroxide, there's 25 mils of that, but we don't know the concentration of that. That's what we're going to calculate. So we can only start with the one we know the concentration of. So in an exam, I would underline the one we know the concentration of, which is the hydrochloric acid, and we know the volume of it. Now this is, be careful here, this is where some students transpose the numbers here. This is the volume of the acid, that's the volume of the alkali, 25 mils. So we start here, so we've got 20 mils of, means times, of a 2.20 moles per dm cubed. We haven't got a dm cubed, we've only got 20 mils, so we divide that by 1,000 to get it into moles per centimetres cubed. So leave that in your calculator. So this is 0.044 moles of HCl, and that's in our 20 mil volume. So don't forget why we're actually doing these calculations. So in that 20 mils that we added to the 25 mils of lithium hydroxide, we added 0.044 moles of HCl. Now this one's nice because it's 1-to-1 reaction, so therefore we know that we've got 0.044 moles of lithium hydroxide in our 25 ml pipetted sample that we started with. So that's no good to us because we want to know the concentration, so we can't stop there, okay? But we have got 1 mark here. We've got to convert that into concentration, and concentration is always in moles per dm cubed, or it could be grams per dm cubed, but this time we're working in moles. So how do we convert that into moles per dm cubed? So you should leave everything in your calculator and you will get the right answer at the end. So this is moles per dm cubed. Shorthand is mole dm to the -3. So that's both our marks there. So that's the concentration of the lithium hydroxide. For the next question, there's an easier way of calculating this. So if we look at it, the question, we want to try and find out which one of these hydrates contains 45.9% of water. Okay, so is it that one, or that one? So you can see that each time we've only got one lithium, one chlorine, so just do one calculation. So the first one I've done, so lithium chloride with 1 water of crystallization. So water, the MR of water is 18, so this is 60.5, the MR of that. So 18 divided by 60.5 times 100 is 29.8, so we know it's not that one. So the next one, with 2 waters, we've already worked out the MR with 1 water, so we just do 60.5 plus another water, 18 plus 18. So we know that one's 78.5, the MR of that is 78.5, and so now we just do 18 divided by 78.5. Times it by 100. Times it by 2, because we've got 2 waters. So we've got 18 times 2 here. And you will see that we've actually, on the second attempt, we've got the answer. So we've got our 3 marks. We don't need to do the third one, obviously, because we found the answer. For this next question, all we need is our equation here, moles equals grams over MR, to work out that which ones have the same number of molecules, so the same number of particles. So don't forget that 1 mole of any substance has 6.02 times 10 to the 23 particles. So that's a definition of 1 mole of anything. So here, how can we work out how many moles we've got? We need to divide the grams divided by the MR. So here, I've just done all the work for you here. So these are the MRs of methane, oxygen, don't forget, 16 times 2, ozone, 16 times 3. So just work them out and then you can see which 2 contain the same, that's the same number of moles. So therefore it's methane and SO2. So nice easy 2 marks. You should be getting a bit more confident now, so have a look at this question, pause the video, have a go, and then play the video for the answer. Just need the same equation again, moles equals grams over MR. We've been given grams, we can work out MR. We always have a periodic table with the exams. So what is the moles of calcium? So we've got 4.8 grams divided by, in this case it's the AR of calcium, which is 40. So we've got 0.12 moles of calcium. And number of moles of water, we've got 3.6. We've already worked out the MR of water, which is 18. So we've got 3.6 grams divided by 18 is 0.20 moles. So that's our 1 mark. Got to get both correct for that mark. Which reagent is in excess? Which have we got most of? We've got most of the water. But we've got to look at the stoichiometry. 1 mole of calcium reacts with 2 moles of water. So is water in excess here? We know here it looks like we've got more moles of water, but actually, if we look at the stoichiometry, how many moles react? Moles of water to moles of calcium, we need 2 moles of water react with 1 mole of calcium. So therefore, have we got 1 mole of calcium? No, we have 0.12 moles of calcium. So 0.12 moles of calcium needs 0.24 moles of water. Have we got 0.24 moles of water? No. We have 0.2 moles of water. So we haven't actually got enough moles of water to react with 0.12 moles of calcium. So initially it looks like that the moles of water is in excess, but actually when we look at the stoichiometry of how it reacts, it's actually calcium as 0.12 moles of calcium needs 0.24 moles of water, and we don't have 0.24 moles of water, we have 0.20, so the calcium is in excess. The next part of the question is a little bit more tricky, and we've got to calculate the mass of the reagent which remained. Now we know now that the calcium is left over. How much calcium did we add? We added 0.12 grams, but we now know that is too much calcium, because that much calcium in that much water won't all react. So let's go back to the number of moles of water. We know that 0.02 moles of water will react with 0.10 moles of calcium, because it's a 2-to-1 ratio. So we know the calcium is in excess, so how much calcium will 0.20 moles of water react with 0.01 moles of calcium? We added 0.12 moles of calcium, so therefore we have 0.02 moles of calcium unreacted in the mixture. So 0.10 would have reacted with the 0.2 moles of water. We've got 0.02 moles unreacted. That still doesn't answer the question. It says the mass in grams. All right, so mass, we've got to go back to our equation. We have moles. We have the MR or AR in this case. So we've got to multiply 0.02 times 40 to give us the mass in grams. So we would actually have 0.8 grams left over. This is of the calcium. So that gives us the extra mark here. Have a go at this question now then. Pause the video so that you can have a go, and then I will then tell you how to answer this. So many compounds have waters of crystallization. So iron sulfate is one of them. And so how do we calculate that? Well, we can get some of the compound and then heat it up gently, and then the water will evaporate, and we're left with the anhydrous version of the compound, and we can work out how much water has been evaporated off. So just gently heat it, and that will, and do a mass before and then a mass after, and keep heating it until you get a constant mass. So here they've done it all for us here. So and also what's nice is they've given us the MR of 1 mole of water. They've also told us that we've got 37.2% of water in our compound, in our hydrated salt, and the mass of the water in 100 grams, so 100 grams, 100%, so is 37.2 grams. So you can see they're the same, because percent is out of 100, how many grams in 100. So how do we work out the number of moles of water in 100 grams? It's easy. We've got our equation here, moles equals grams over MR. They've already told us the MR of water. We know the grams is 37.2. Divide that by 18, and you should get 2.07 moles. Keep it to 3 significant figures. So therefore, what is the mass of iron sulfate? So this is the anhydrous without water. So you can see here, I'll just draw a little diagram here. So 100 grams you started with, heated it up, 37.2 grams of water left. So it's 100 minus 37.2 equals 62.8 grams, and that's of the anhydrous iron sulfate. It hasn't got any water in it now because it's all left. So we've got 1 mark here, we've got 1 mark here, we've got 2 marks out of 4. Now again, they've been nice to us, they've given us the MR of iron sulfate. So what is the number of moles of iron sulfate in 100 grams? It's the same old equation, 62.8 moles equals grams over MR. This time the MR is 152. So again, keeping it to 3 significant figures, that's how many moles of iron sulfate are in our original mass. Now we've got to try and work out what X is. So we've got 3 marks here. How do we solve and find out how many waters of crystallization are in iron sulfate? What is X? So if we look at our mole ratios then, we've got 2.07 moles of water to 0.413 moles of iron sulfate. How do we solve that into whole numbers? So where's the ratio? So divide it by the smallest. So divide that by 0.413, and we end up with 5:1. So there are 5 waters for every 1 iron sulfate, so therefore X is 5. We're rounding this up a little, rounding it down, sorry, 5.01 was the number that came out of my calculator, so X is 5. For this question, we've got to calculate the percentage yield. This one's worth 4 marks, look. So pause the video, have a look. It's another titration, but this time they've given us all of the values that we would need, including the equations. But this time be careful, because at the end here it says calculate the percentage yield giving your answer to 1 decimal place. Okay, so that's worth 1 of these marks here. If you don't give it to 1 decimal place, you will lose a mark there. The start of this question explained how the lithium sulfate was made by titration. It's hydrated lithium sulfate. So we've got lithium hydroxide in the conical flask, and in the burette we've got sulfuric acid, and we've got an indicator, and then the volume of the sulfuric acid needed to just neutralise the lithium hydroxide is noted, and then we would then repeat the experiment without the indicator, and then add the same volume of acid, and then we would then evaporate the solution, evaporate the water off until we get to the crystallization point. We would put a cold glass rod in, and if crystals formed on the glass rod, then we know we've got to the crystallization point, and then you would leave that to dry overnight or in a warm oven, and then you would get your pure dry crystals of hydrated lithium sulfate. I'm not going to answer that part of the question because I'm looking at the math calculations today. Now, the first part of this question is fairly easy because we know the volume of the known one, which is the lithium hydroxide, is 25 mils. We know the concentration of it, so start there. And so volume times concentration over 1,000, that gives us how many moles of lithium hydroxide are in our 25 ml sample that we took, which is in the conical flask. That was titrated, wasn't it, with the sulfuric acid. So that's how many moles we had in there. Now we go to the next part, which is a little bit more tricky, and we've got to look at the fact that 2 moles of lithium hydroxide make only 1 mole of lithium sulfate. That lithium sulfate then reacts with water to make our hydrated lithium sulfate salt. So what's the stoichiometry? Well, it's 2 moles of lithium hydroxide make only 1 mole of lithium sulfate. So what have we got to do to this number here to get to this? So 2 moles make 1 mole, so 0.062 moles would make 0.031 moles of the hydrated lithium sulfate. Just divide it by 2 because it's a 2-to-1 ratio. I know there are 2 equations here, but just follow it all the way through and you'll realise it's actually a 2-to-1 ratio. Now, if you get that wrong here, it's not the end of the world, because what you can do is get error carried forward all the way through. So don't worry if the stoichiometry is wrong. You'll end up with getting 3 out of 4 of the marks, hopefully. It's always worth giving these questions a go because you'll always get some marks. So for the next part of the question, we need our equation, moles equals grams over mR. They've given us the mR. We have moles here. So we rearrange this equation and we get grams. So you can see here I'm still working to 3 significant figures because I'm going to look at that at the end. I'm going to go back to my original question and it says only 1 decimal place. I'm not going to worry about that for the minute. So now I'm going to get to the last part, and it's my percentage yield. So this is what I should have got. That's my theoretical yield, 3.97 grams. Have I got 3.97 grams? No, I've only got 2.20 grams. So it's 2.20 is our actual yield divided by our theoretical yield, which is 3.97 times 100. And now just be careful with this last part because we're answering to 1 decimal place. So in my calculator, I've got 55.443548. We don't want all of that. We only want 1 decimal place. So I'm going to round that up to 55.4%. So that's 4 marks. Here's another question, this time looking at gas volumes. So pause the video here and see if you can do this, and then I'll go through the answer. So key things to look for in this question then. We know this many grams of sodium sulfite. Calculate the maximum volume of sulfur dioxide. So this is what we're trying to calculate. They've given us the MR here, so that's good because we need that to work out moles. So you can see here I've reminded myself the important bits of information I need to solve this issue, this problem. We've got 3 marks here. So moles equals grams over MR. So we've got grams, we've got 3.15, we've got MR. So if you don't know what to do, and you can't do anything more, just always work out moles. If they've given you grams and they've given you MR, or you've got a periodic table, you can work out MR, you can guess at least 1 mark out of 3. So always have a go, always calculate moles, because it's very simple. It's just moles equals grams over MR. And then that might be all you can do, but at least you've got 1 mark. Now, the stretch and challenge part of it is to work out how many moles of sulfur dioxide. So this is moles of the sodium sulfite. That makes, so 1 mole of sodium sulfite makes 1 mole of sulfur dioxide. So therefore, how many moles of sulfur dioxide have we got? Well, we've got the same. So that's my second mark, looking at the balanced symbol equation. They've told us the hydrochloric acid is in excess. We don't need to worry about that. Now what we need to do is convert moles into volume, because the question is asking us what is the maximum volume at room temperature and pressure of sulfur dioxide. So we go to our balloon. Here, 1 mole of any gas occupies 24 dm cubed. We haven't got 1 mole, we've got 0.025 moles. So all we've got to do is do 0.025 times, if we do 24, we'll keep it in dm cubed. Therefore, we have 0.6 dm cubed. Or we could do 24,000 and we would have 600 centimetres cubed. Depends which way you'd rather work. Either one is correct. So we've got our 3 marks here. It's really important though that you put units. You can't just put 0.6. You would lose that mark, because 0.6 what? You know, you need to say it's 0.6 dm cubed, or you need to put 600 centimetres cubed. Units are required here. Here's another titration type question. So have a go at this, pause the video, and then I'll work through the answer. This one's slightly different in that we haven't got an unknown. This time we know the concentration of the acid and we also know the concentration of the alkali. Now what we're going to do is work out which one is in excess. So we can start with the first part of the question. How many moles of sulfuric acid were added? Well, we've got the volume, we've got the concentration, we can work out moles. So that's nice and easy for the first mark. 20 times 0.3 divided by 1,000, because we've got 0.3 moles per dm cubed, and we've only got 20 mils of that. So this is how many moles of the sulfuric acid. So that's our first mark. How many moles of sodium hydroxide were used? Is that the same equation used? Like 40 times 0.2 over 1,000. So that's how many moles of sodium hydroxide. So which reagent is in excess? Now we need to look at the stoichiometry. 2 moles of sodium hydroxide react with 1 mole of sulfuric acid. Because it's a 2-to-1 ratio, you can see that we've got 0.006 moles of sulfuric acid. they would react with 0.012 moles of sodium hydroxide. Have we got 0.012 moles of sodium hydroxide? No, we've only got 0.008. 0.008 moles of sodium hydroxide reacts with only 0.004 moles of sulfuric acid. So therefore, the sulfuric acid is in excess. So now you can see we've got 4 marks. There's 1 extra mark to obtain. And you can only get this mark if you've got this III mark correct. So now we know that the sulfuric acid is in excess, then it is not going to fully neutralise all the sodium hydroxide. There's going to be some acid left over. So therefore, the mixture is going to be less than pH 7. It's not going to be neutral. It's going to be less than 7 because we've got more acid than alkali. So the pH is going to be acidic. So now we've got our 5 marks. Here's a nice empirical formula question. So again, pause the video, have a go, and then I'll go through the answers. So first part of the question was worth 1 mark. How do we know the acid contained only carbon, hydrogen and oxygen? Well, as they've told us this much grams of carbon, this many grams of hydrogen and this many grams of oxygen, add them up together, that's 5.8, and it says here it's 5.8. So therefore the numbers add up, so therefore it must be only carbon, hydrogen and oxygen. So now with that information, we can now work out the empirical formula. Now don't worry about this, the word maleic acid. They'll always give you something you've never seen before to see if you can apply your knowledge to new situations. So you don't even know what the formula of maleic acid is. You don't need to know it. You just need to work out the empirical formula. And then we can then work out what the molecular formula is. So don't worry if you've never seen maleic acid before. Just follow the same steps as what you've always done. So again, we've got our moles equals grams over mR, or in this case it's actually AR, because we're looking at the moles of the atoms here. So we've got grams over, so we've got carbon 2.4 over 12, hydrogen 0.2 over 1, and oxygen 3.2 over 16. And you'll see, look, that they've got the same mole ratio. So therefore, the empirical formula is just CHO. Because if we followed the last step, which is divided by the smallest, which is 0.2, we're dividing them all by themselves. So we've got, it's a 1-to-1-to-1 ratio. So you can see now we've got 4 marks. Now we do the last mark and work out what the molecular formula is. So the simplest whole number ratio is CHO. That's obviously not what maleic acid is. Have a look at the next part of the question. So the mass of 1 mole of maleic acid is 116. What is its molecular formula? So we know what the empirical formula is now. So now we need to add up the ARs of the empirical formula. So CHO, the MR of that is 29. So 12 plus 1 plus 16, so add up all the atomic masses. And we know that the molecular formula, 1 mole of maleic acid is 116. So 116 divided by 29, which is the empirical formula, is 4. So therefore, we know we've got to multiply everything by 4. So it's C4H4O. So we've got 2 marks there. Now it says, the last part of the question, it says it's dibasic. What does that mean? It means that 1 mole of acid produces 2 moles of H plus ions. So we've got to find out what its structural formula is. So here you can see I've drawn the displayed formula of this acid. This is actually maleic acid. So you can see these are the two protons that come off when it ionizes in water. So that's worth Rx, an extra 2 marks. Just realised I made a mistake there. So I went back to the formula C4H4O, and my structure had too many hydrogens, so therefore it must have a double bond in the middle there. So it must be this structure, because that's the only one that would fit that molecular formula. C4H4O4. That's where I've gone wrong. O4. C4H4O4. So that last question is obviously much more of a stretch and challenge for the more able candidates. So it's always, you always have time, hopefully at the end, to double check, make sure you haven't made silly mistakes like I've just done. Forgot to multiply the oxygen by 4. And just check over your work, and good luck with your exams.